So this presentation is about dependent type and more particularly dependent types for practical use. What do I mean by practical use? I mean use in industrial software or use where proving statements is not the focus, but using software or using programming languages is the focus. I wasn't really sure how to structure this thing. And the one thing that I wanted to keep in mind is I want to make this useful for the most amount of people without making it useless for the people who are here. And that's why I want to focus on practice rather than theory, because I am sure a lot of you are very familiar with formal methods and how to prove statements, but there's another side to this that we don't necessarily get to experience when we're in academia, and that's to write real world software for running servers and big machines that rely on millions of customers, etc. And on the other hand, I want this to be useful for the lay people, let's say, who are not familiar with formal methods, who are just hearing about dependent types or more generally about typing or complex type systems, things like Rust or things like Scala or things like Haskell. And so those people are mostly usually people who are familiar with things like object-oriented programming or programming in general. So I will assume that you know about object-oriented programming because it's a very common way to program nowadays. And you will see mostly on the code samples that or the vocabulary I will use to describe programming languages that do not feature dependent types. I will also assume that you're familiar with generic or polymorphic types, which is the practice of programming with types that are over which we abstract. For example, if you asked you to reverse a list, you will use a polymorphic type saying, I don't actually care what is inside the list. I only care that it is a list, and the type of the elements can be abstracted away. Often when we talk about dependent types, we talk about the type theory that underlies the dependent types. For this presentation, we're not going to talk about the type theory because I want to really show the focus on the usage of dependent types and not why they work. And finally, we're going to talk about, we're not going to talk about functional programming directly, but a lot of those ideas are tangential or related to functional programming, in that the programming language we're going to use today, Idris, is a functional programming language. And most programming languages that feature dependent types are functional programming languages. That doesn't mean that they have to. This is a completely different discussion. But as an audience, I expect you to be at least somewhat curious about functional programming. So Keith introduced myself as a PhD student. I'm going to expand on that to explain where I'm coming from originally, and this should give you an idea of a motivation for why and how we're going to approach this topic. So before I was a PhD student, I was a software engineer. I worked on a number of areas of software. I was a mobile application developer working with Android and iOS. I've been working on game development, making games for mobile platforms as well. And I've also been working as a backend software engineer, writing servers, microservices, APIs, etc., and documentations. And then I transitioned towards research, and my main areas of research are dependent types, in particular, the ergonomics and the user experience of programming and programming languages. And those hinge on different type theories that we can use in order to express different kinds of programs, and that we can, and which properties are useful in order to write programs, not only describe properties, but also have a good time while we are punching in the code onto the computer. Dependent types are, I'm going to split the motivation for dependent types into two areas. There are areas where we need dependent types in order to express something, and areas where we want dependent types, but they're not necessary. They're just a very nice bonus. And I'm not going to explain quite yet what dependent types are. I'm going to explain in terms of what they provide us in terms of solution to a problem. So here's a problem. we want to avoid crashes or runtime errors. Here's a very simple program in Java that creates a new list and then tries to access the third element inside the list. If we write this program, our computer will not complain. I will be happily compiling this into bytecode, and then we can execute this bytecode. And the execution of this bytecode will result in a runtime error. While runtime errors are not necessarily a problem, a lot of times you want them, for example, to protect areas in memory or to crash early when something is fundamentally broken. In this case, it feels like the computer should be able to tell us that something wrong is happening before we run the program. And we can get to this conclusion just by looking at the code. We see that we are creating a list. We're not putting anything inside it. And then immediately we're trying to retrieve an element out of it. That's incorrect, right? That is very, it is very obvious what is the problem here. The problem is that we have not put 3 elements in there. So there are 2 solutions. Either we force the user to put at least 3 things, or we stop the compiler from allowing to call the function get3 because we don't have 3 elements in them. And we're going to see how we can solve this with dependent types. Another problem that is slightly related, but related in the way it manifests, but not related in the way we experience it, is to constrain existing programs that expose an overly general API. If we look at this example, we have a date formatter object that takes a string and creates a new format. If we just look at this definition, at its definition, we only see that it takes a string and we don't see the structure that is required from the string. And so in the second line, you can see that there's nothing stopping us from calling this method with an incorrect string or an incorrectly formatted string. Now, this will also result in some sort of runtime error or incorrect behavior, but that's not the thing I want to focus on. What I want to focus on is the user experience of seeing a function from string to format and not being able to tell what kind of string goes in. So we're going to look at those 2 examples. To avoid crashes, we can do so in a programming language such as Idris, which has dependent types, by saying, we're not going to use lists. We're going to use a version of lists that exposes in its type the number of elements it contains. In this example, I have a vector cars that contains 0 elements, and I'm calling the function index that we're going to see very soon that says retrieve the 3rd element out of the vector cars. And that results in a compiler error. The compiler is able to see what it previously was not able to see by saying, I was expecting something of size 0, and you got me something of size successor of length. I'm going to explain how this error message reads in a little bit. The other aspect is if I copy the same API as before for string format, we see that if we misuse the API, we get another error. It says cannot find implementation for string format. So those are 2 examples where you need dependent types in order to solve some problems. And the way they manifest is that dependent types allow you to express programs or properties within the type of your program. Now, what are the cases in which you want dependent types? Where those cases, they mix with the cases where you need them. So we are going to see an example where not only they are useful when you want them, but even if you don't use them, they provide some benefits. And the benefits are, I'm going to summarize them as follows. Because the types are much more expressive, you have a lot more information inside the type. And so you have a lot more tools to read and understand programs. Because the types have much more information, you have more precise error messages about what is going on. The third one is not necessarily related to dependent types, but is related to a expectation that dependent types have nowadays with editors such as Coq, Agda, and Idris, where you have some sort of interactive editing that tells you something about what you're doing, which is very important because, as we'll see, types can change as you're writing your program. And it's very important to be able to tell when those changes are occurring. And finally, because they are so expressive, you gain a lot of flexibility when using dependent types. So here's a small demonstration of what we are looking at. Here is a terminal. I hope the font is big enough. Please tell me if it is not. I just realized I don't have the chat window because of the screen sharing. Here we go. And here I have a vector of names, and I have a main function. The syntax is very similar to something you would see in Haskell.
Andre, sorry, could I just jump in here? It's, all I'm getting is saying Idris demo here on the screen that we've got here.
Let me.
Oh, there we are. That's it. Perfect. Thank you.
Is this working properly? There we go.
Yeah. Thanks.
So in this program, we have a vector of 3 things, and we have a main function. And on the right side here, we have a REPL in which we can evaluate programs. The first thing I want you to notice, if I replace this 3 here by a 0, I get a type error. And the type error says cannot unify s of length and 0. And that's because 0 is not 3. Which is fairly obvious to say, but you have to understand a little bit how this is implemented in order to make sense of this error message. This is actually a problem that a lot of people are interested in, is how to better express error messages in dependently typed languages. But this is, if you understand what's going on, fairly obvious. And we're going to explain immediately what's going on. Numbers in Idris are represented as nested successor of 0. And so the number 3 is represented as 3 nested successor of 0, because the successor of 0 is 1, then the successor of 1 is 2, and then the successor of 2 is 3. And because we have created here a vector of 3 things, it is the successor of 2. len here is actually 2. And the problem is, well, successor of 2 is not 0. And so the fix here is to get the correct length, and everything works fine. Now, if we go to our REPL here, and I do source main, this is our file. There is one function that I would like to see, and in the REPL we can query the type of some function definition. Let's see the type of index. Actually, type vect.index. This is equivalent to the function get we saw before, where it takes a number and it takes a vector, a list of elements, and it returns an element of the given type. But you see that it has this extra argument here, len, for length. And that says the number here has to be bounded by the length of the vector. So if our vector is of length 5, then this number must be between 0 and 4. And if it's not, then you have a type error. And so we can express this by saying print line index of 1 of names, and this type checks correctly. And if I use a bigger number like 5, we get an error. But if I keep 1 and I run the file, I get the correct name at. So that's pretty good. We are now able to detect the problem that we've defined earlier. And you've noticed I've started using some keyboard shortcuts. Those keyboard shortcuts are instrumental to using your editor or using Idris. And something that we've successfully managed as a community is developed a language server protocol for Idris that allows you to use almost any editor that you want in order to obtain those features, as long as it supports LSP. What about the other problem? The other problem was about string formatting. So I don't actually remember the name of the function, but I can do this, and I can do, I think the module is called data, not data, date. There we go. So I can do browse in my REPL and find the API of date, and I'm looking for format string, which is the function that will take a string and return a date format. However, you see, format string is not plainly a function from string to date format. It takes another argument. And this is an implicit argument that says, ensure that the date format is correctly formatted. So if I do format string, and here I put an empty string. Does this work? Format. I get a type error because it says I cannot find implementation of string format, which means Idris cannot prove that this string is a valid string format. However, if I do year, 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 month, month, day, day, the error goes away because Idris was able to prove that this is a correctly formatted string. And that rules out a lot of errors as well, because if I make a typo here, then this is not a correctly formatted date anymore. So we've solved the ability to, well, we've been able to remove errors by saying only index lists if you have at least that many elements. And we've been able to, in the type, express this constraint that our date format must be a specific kind of string, not just any string. I'm going to move here. Oh, that works. Excellent, excellent. So we've been very very loose with our definition of dependent types. Just said dependent types solve this, but we haven't actually explained what they are. And the way I'm going to explain this is by, well, I'm going to hinge on the fact that if you hear dependent type, you might think that something depends on something else. This dependency can be seen in other programming languages. So in a programming language, in general, we have both types and we have terms. There are languages that don't have types, like JavaScript. But we're going to focus on languages that have types and terms that inhabit those types. So if I say there is a type Boolean, it also means there are two values, true and false, that inhabit the type Boolean. If we look at those languages that I've listed here, those languages and language features, we see that if you have a language like C, which has a very weak form of typing where the types represent memory sizes, basically, we can't really get much dependency. We do get a dependency that is fundamental to programming, though, and that's terms depend on other terms. So if you create a new program, that creates a term, and then you can grow your program by relying on your previous definitions. If you have a programming language such as Java that has generic types or polymorphic types, you have terms that depend on types. So that means that the terms you define are different depending on the types they manipulate. An example of this is an interface. If you look at the iterator interface, one iterator, the term that implements iterator, is different for array lists or for linked lists, because array lists are contiguous and linked lists are pointers that follow each other. If you look at Haskell type families, this is a feature that allows you to write small programs that look at types and generate new type definitions. It's like a very sophisticated way of doing a type alias. And for example, one way you can use this is saying, if I am looking at a list of ints, do not use a linked list of ints because that's very inefficient. Use directly a buffer of integers, like a contiguous memory buffer of memory, just for efficiency reasons. And if you're not looking at a list of integers, just use a linked list normally, because all the other cases we don't really care about. And in this case, we have types depending on types. Those are programs that take as argument types and return types. Idris has dependent types, which means types depends on terms in the language. So just like I said, you have values Boolean that inhabit the type, values Boolean like true and false that inhabit the type bool. It means that we can construct types from the values true and false. And so this was the very long-winded explanation. There is actually probably a much clearer explanation if you're used to debating programming languages, and that's programming languages often advertise themselves as having first-class X. For example, oopsies, here, first-class types. So dependent types is having first-class types. And if we move this first-class X definition to other languages, we see that C, for example, has first-class pointers. What does that mean? It means that you can create pointers, return by allocating memory, return pointers, or take pointers into argument. Java has first-class object because you can create objects, you can return objects, take objects to argument, etc. Haskell as a functional programming language has first-class functions because you can return functions from functions, you can take functions as argument. And Idris has first-class types because you can create new types, return new types, take types as arguments. And this manifests itself into programs. You can write programs such as this one. And I don't expect everyone to understand the syntax. I just want to show this difference between things that have a colon and things that have an equal. Things that have a colon are defining types, and things have an equal are defining the body of the function. So the top left, we're doing return type, and we're saying return type is a function that takes a Boolean and returns a type. And underneath, we analyze the value of the Boolean. If it's true, we return the type string. If it's false, we return the type int. Note that those are not values of type string and values of type int. They are the type. And then how do we use this? We use this by calling it inside the type signature of another function. And depends is a function which type uses the definition of return type. And furthermore, it takes as argument the argument of depends. So we've named here the argument of depends as b, and we've passed to the function return type, and that informs us of what we need to return in order to implement this program successfully. So I'm going to quickly show you what this looks like. Return type is bool, so this is going to return a type. I'm going to simply copy this and do true, and if it's true, it's string, and if it's false, it's int. And depends takes a Boolean and returns the result of calling this function here with this argument. And now is the first time we're going to see interactive programming for real. We're going to create a skeleton definition by typing a keyboard shortcut. Then we're going to ask, what is the type at this point? And it's going to tell us, we don't really know. We only know that it depends on b. Because of this, we're going to analyze the value of b. And b can have two values, either it's true or false. And with this extra information, we know that in the case of false, we return a number. So I'm going to return 42. And in the case of true, return a string. And this is hello. And this very simple example showcases how we can use dependent types in order to, how do you use dependent types in order to return multiple things by creating a new type and using it inside a type signature. This is some form of compiler level function. Let me go quickly to the slides. So another thing we can do with dependent types is we can make use of the additional flexibility in order to implement things that were previously impossible to implement in a type programming language such as Java or even Haskell, some, well, old style Haskell. So heterogeneous lists. This is something I hear complain about sometimes because as a counterpoint to as a counterpoint to typing, because sometimes the data that we get from the real world is messy. It's mixing up data, it's mixing up semantics, it's not very clear how you're supposed to use it. And it's not very clear how you're supposed to program against it. There's no structure to it, or it seems like there's no structure to it. So if you have this list is a list of three things. It contains a string, it contains a number, and it contains an object user. If you only had the API that you have in a programming language such as Java, you only have one type, which is supposed to represent the entire list. But this is not accurate. This is not accurate representation of the list. The list contains three things. So you can make up some syntax and say, well, I would like something a bit like this, where I can tell that the first element is a string and the second element is an int and the third element is a user. But then it's not really clear either how you're supposed to index into this list, because if I say, get me the element at index 1, I mean, it's a number, but how do you know that this number corresponds to integer? Us as human, we can see it because we can see that at index 1, we said that there was an int, and then we look at the data, then at index 1, we have an int. But that's not very obvious for the computer. And then we had to write a program that represents like all this general, all this passing of indices saying, are you looking at the index of the type? Are you looking at the index of the value? Tell me what the value of the thing is. What we just want is do something like this. We just want to have our list, our value, and say index at this, and then return 1, and don't have to check for what is the type of the thing. So I'm going to do this. Let me just quickly check that it's open somewhere. This, no, is it? Oh, did I lose it? There we go. Apologies for the small delay. There we go. Let's show the terminal, and here we are. So I've loaded a file that contains the definition for a heterogeneous list. And this heterogeneous list contains in its definition a vector of types. And those are the types that are living inside our heterogeneous list. What we want to write is a function like this, index at, because this is what we want to do with a heterogeneous list. We want to obtain an element inside it. Just like before with vectors, let me just show you again, type data.vect, actually vect.index. We want to use a finite type, that is bounded by the length of the number of types, because we know if our list contains n types, it means it contains n elements. There is no sense in indexing beyond n. We're always going to look at n elements. This is going to be fin of n. Then we're going to have a heterogeneous list of types, and this is going to return something. Here, this is where we have a dependent type showing up, or a dependent program. The return type of this function depends on two things. It depends on the index here, and it depends on the types here. So what are those types exactly? I'm going to call this ret. Those types here, can I get the type of this? No. Can I get the type here? No. What we want those types to be is we want them to be a vector of n types. We're going to write this as an implicit hidden argument and say types is of type vect n type. There we go. Meaning that the argument of heterogeneous contains n types. Now, if we look at this, we're going to look at something that's very familiar. We're given an index and we're given an element, a vector that contains exactly that many values. And we're expected to return a type, right? Because we're in a type signature, we expect to return a type. Doesn't this look familiar? This can be implemented using index. We can index this list of types, saying, oh, if I'm looking at the third element, then the third element will be the type of the third type in this list. And I can get this because I have the index available to me here. And I'm going to do this by calling index. So let's do that, index of types. And now we can implement this function. So to implement this function, I'm going to use our interactive editing things. So first thing to do is create a skeleton definition. If we look at our type here, we see that we don't have enough information to know what is the type of this. We just know that this type depends on index of types. So we are going to analyze the index. And FZ means that we found it. It means that we're done looking at element, and FS means that the element we're looking for is not here yet. It's further down the list. This is very similar to what you can see as a proof by induction, where you say this is the base case and this is the inductive case. Base case is we found it. Inductive case is we haven't found it, but it's later. And if I look at the type, we see we still don't have enough information. We need to figure out what the types are. For this, I'm going to match on the vector itself. And now I can ask what is the type here, and it says, I found it. Your vector is actually not empty, which means it contains a value. And I figured out that if you're looking at the elements here, the element has the type A, and the element contained at this position of the vector is also of type A, right? Here's the value that's in the vector, and here's the return value we expect. So we can simply return val. What about this? Well, same thing. We don't have information about the vector, so we need to match on the vector. And well, actually, that was not even necessary because, well, it's not necessary, but you can see that this expects us to return vector of index of y, so something that is inside this index. But now we need to look at the rest of the vector because we've looking at vectors as linked lists, and so we know that it's not in the head, which means it must be in the tail. And for this, we're going to make a recursive call with index at y and x. Great, and that works. So I can probably write an example. This is not rehearsed, by the way. I have no idea if this is going to work. I mean, I'm fairly confident it's going to work, but example. And this is going to be heterogeneous of string and int. And for the fun of it, I'm going to put type here. So this string contains three things. It contains a string, sorry, this list contains three things, a string, an int, and a type. And if I try to fill it up, I can do it by doing this, hello, 32, and then nat, which is going to be natural numbers. Does this work? Oh, incorrect syntax because I've used the shorthand syntax rather than the syntax I've defined earlier. And this is a typo. And this is also a typo. Here we go. And so there are two crazy things. So the first crazy thing is that we are able to define heterogeneous list if we define the structure in advance. And we're also able to use types are normal values. We can just return this nat type and say, expect that the third element is a type, and here returning natural numbers as a type. There's one more thing I want to show you, and that's as interactive editing. Those question mark things, they're called holes. There are placeholder programs where you can just query the program and say, what is supposed to go in here? And as you can see, what is supposed to go in here is a heterogeneous list of three things. Now, I can use a keyboard shortcut to say, please tell me more about this by attempting to implement this yourself. And here it came up with two answers, but the first one is the one that has most information. and it says, oh, I know that you need at least two elements in this list. So here's the first one and here's the second one. And now if I look at the type here, I get a different answer. This is not a list of three things. This is the first element of the list. So that we can put hello. And then we can look at this thing and says, oh, what is supposed to be here? Oh, it's supposed to be in. So we're going to put 33. And then we can go here and see, oh, what do we need here? We're not quite sure. This is a list of one element and it's a type. So I can do the same thing. I can do, please refine this definition. It says, oh, if you want a list of one element, you just need a cons and then one empty, and then you're done. And then I can ask the type, and it says the type here is type, so I'm going to put natural numbers. And this is a very great way of implementing your program interactively so that you always know what's going on and you always know what you're supposed to do. And when the compiler knows about it, it will tell you and will do your work for you. We're going to do one more example because I have a little bit of time. We're going to do append of two heterogeneous lists, right? And append of two heterogeneous lists will rely on a compile time concatenation of the indices, or rather the structure. So if I have, for example, a heterogeneous list that contains string int, that's our first heterogeneous list, and the second one contains nat and list of nat, that's our second heterogeneous list, then the result of concatenating those two will be string int nat and list nat, right? And we express this by saying those xs and ys represent the structure of the heterogeneous list, and the resulting structure is the concatenation of the two indices that represent the structure of the list. And we can do this almost automatically by saying we're going to match on this, then we're going to analyze the first argument, then I'm going to say, please generate the definition for this. And it comes up with y, and then say, please come up with the definition for this. And it comes up with a program. And I have not typed, I haven't typed a single line of code. I just let the computer do its work by saying, figure out what you're supposed to do with the implementation that is given here. All righty, so let's move on to the final demonstration or final motivation. I've had this question asked to me last week on Discord. How do I sometimes return a value and sometimes return an array, depending on the data that I'm looking at? This was in the context of parsing some data from the network. Particularly, it was parsing a binary format. But it was not any binary format. It was a binary format representing tracks and playlists and songs. And we knew in advance that there were basically two kinds. And whenever we look at one of them, we don't really have to check if it's the other. We already know. So intuitively, this person came up because they were accustomed to TypeScript. They came up with this solution. I want to write this program, but in the language they were working on, this was not a valid construct. It was C#. In TypeScript, that would work, but you would have the constraint that whenever you are dealing with a value of type value return, you'd have to check if you're either an object or a list of objects, which is not really what we want. We know in advance, if we've already done the parsing, we already know which type we're looking at. So there's no point in having to check over and over again whenever you're done with parsing. The subtlety is, how do I return two things depending on the data that I'm looking at? There is, in this previous example, we never know which data we're looking at. But in this case, when we know the data we're looking at, we have two different types. So what we really want is something like this. This is not real code, this is pseudocode, but we want something where if we look at the data, then we know that we're an object, or we know that we're a list. And this is you notice this is a program inside a type. And because we have first-class types, we can write this program in Idris. So I call this the JSON demo because this was in the case of parsing some JSON data. Let me just check that I have the code available right now. Yes. Yes, this is it. So same thing. I have as examples, so I've only imported this file that allows me to define JSON. Oh, can everyone see? Yes, everyone can see. JSON data structures. And here are raw JSON files. So the files that we're looking at, they come from the network, and they have this structure. They have a field type with a playlist in case of a list of music tracks, or they have a type music, in which case they only contain one track. And so the question is, how do I represent this fact that whenever this is playlist, I should expect a list, and whenever this value is music, I should expect a single track. So here, playlist JSON and music JSON are the same, but as JSON objects, so they're already parsed. And here's the data structure that represents music tracks. And this is the function at the type level that we're going to execute in order to figure out which of the two we are looking at. So the thing we have to do is inspect the JSON object, extract the type field if it exists, extract its value as a string if it exists, and check that it is a music track. In that case, we return the type of music. Otherwise, we still inspect the object, we still inspect the type field, we still inspect its value as a string if it exists, and if it equals playlist, then we know that we are meant to expect a list of music tracks in its object field. Here I've written two utility functions that inspect the JSON object and parse them as either music tracks or lists of music tracks. And here is the function. So we're going to implement this together step by step, because it's going to be informative. We're going to learn something. So the first thing to notice is that we have an argument, which is a JSON object, and the result is a maybe of a JSON object. Why is it a maybe? Because we can fail, right? This could be an invalid JSON object. It could not follow the structure we're looking at, which is exactly what I want to represent. Additionally, you can see here, I said if we don't have the correct type, then we have to return a value of void, which means this JSON type is uninhabited, which means if we don't know the type of it, we actually cannot instantiate any value for it. If we build a skeleton definition and we'll look at the type of what the program expects, it says, oh, we have to return a maybe something. Now, here's the funny thing. If I do fill up this program for me, Idris comes up with nothing, or literally the constructor to say, I failed to parse this JSON. This is not what we want. This is a valid program, but this is not what we want. What we want is to have a value whenever this is correctly formed. So we are going to inspect the JSON here. And oops, this is, ignore this. This is just because of my install. And in all those cases, we actually do not care what the value is, because we only return something whenever we are looking at JSON object. This is the shape, this is the format we're interested in. We are looking at JSON object, and the first field is a type. So for all of these, I'm going to simply say, ignore the value and return nothing. What about this? So we still have not inspected our JSON object to figure out which type is supposed to live inside the object field. So we are going to inspect this and say, you must contain two fields. You must contain the field type. Wait a minute. Like this. And you must contain the fields. Do we care about the object? No, we don't care about the object. No, we do care about the object. Yes, because we need to parse the object. So you need to contain the field object. And I've missed a bracket. Here we go. Now, if we look at this, we see that we've made a little bit of progress, but we still don't know which type we're supposed to return, because we've not inspected the value of the field object. So for this, we're going to say the value of this field object must be a JSON string, which is music. And for the second one, it must be a JSON string, which is playlist. And this is a boring error. And I'm going to put this on the next line so that it's more legible. Great. And now that we have destructured our JSON objects and found out that its first field contains a type and that the value of the type is music, we know that we meant to parse a music track, in which case we can call our function parse music because it expects a JSON object and returns a music track. So this is going to be parse music of object. Similarly, if we look at the type of the data here, we have destructured our JSON enough to get enough type information about it to know that this is meant to be a playlist, or rather the value here is meant to contain a playlist of music tracks. And here we're going to be parse list of music tracks. And if we compile, everything works fine. Now as a test, just to make sure that we have not done something horrendously wrong, I'm going to load this file in the REPL and test it. And if I do parse data of, I think it was playlist JSON, we do get a positive response by saying I've successfully managed to parse something, and we get a list of tracks. And if I do music JSON, we do get a different type, even though we use the same function and the same type argument. Like those are two JSON, they're just formatted differently. And if I do parse data of JString hello, I do get an error, not an error, but like information that the parsing of the data was unsuccessful. What else do I want to show with this? Oh, yes. Is this right? So note that this is not going to solve all of your problems, because if you look at the type here, I've put a hole here saying, what am I supposed to do with this program? And if I attempt to parse those, I still get maybes, because even though the type field is correctly formatted, there's no guarantee that the object field is correctly formatted. This is the point of the parsing of the data. So we know what the data is supposed to look like, which informs how we parse it, but it doesn't guarantee that the rest of the JSON object is formatted as expected. It turns out in this case, this is exactly what we wanted to express. All righty. Let's move on to the last part, and that's going to be the libraries. A language is not very useful if it doesn't have any support for its ecosystem. A big part of this ecosystem is the libraries. Idris, thankfully, has a very eager community that provides and builds a lot of libraries for doing programming inside a language that has dependent types and makes use of the features I just demonstrated in order to make the programming of software a lot easier and nicer, and to get the benefits from interactive editing and from a lot of type information from our programs. So I'm going to toot my own horn for a bit and explain one of the libraries I've been working on, which is Recombine. And Recombine is a server library. It allows you to write web servers. As you can see on this picture, the syntax is very familiar to anyone who's been working with servers. It looks like I'm just writing an API, right? Because I'm just saying those are some endpoints, and those are how the server is structured. Those are the endpoint that you can call as a client. But it does a lot more than describe the API. This is an embedded DSL, embedded domain-specific language inside Idris that allows you to indeed define your server in terms of its API and also its implementation by saying, if you follow the whole endpoint, for example, the top /lights/living, it says lens living room light, and that means the endpoint /lights/living is implemented by the lens living room light. That means that you don't have to provide any further implementation than this. The framework automatically performs routing, serving responses, parsing, executing the implementation, etc. You don't have to do any, there is no more code than what is written here. And so that's really nice because you don't really have to do anything to make it work. And because it's using dependent types, you see I have a list of question marks at the top. The question marks are actually saying, please infer the type here. The reason is the types are fairly large because the types perfectly encapsulate what this server is doing, what state it's working on, what its API is, what its return types are, what kind of responses it sends back, etc. In particular, the API of the server is available in the type. So that makes a lot of tools that generate documentation redundant because you can generate documentation by looking at the type. And finally, because of the structure, or because of dependent type, we can use very advanced structures. So in this case, I'm using dependent lenses in order to compose servers together. And you can see at the bottom, I'm instantiating a large server that is the composition of 3 smaller servers, and I'm putting them in 3 different endpoints so that a client can call any one of them. But as a server developer, software engineer, I don't have more to do than create the small servers and then attach them together. And instantiating a server is as simple as saying run the server and pass it the definition that we're given, and you pass it an initial state and then it runs. Here's another one, Coli. This is a command line argument library where you define the command line that you parse. And here this is defining a top level argument. And then those arguments have nested possible arguments. So in this case, we have 2 nested arguments. We have left and right, and them themselves are nested into left and right. And then with this, we can create a dependent function that will implement this API or implement this command line argument by saying, take the command line description turns and run it by the type definition at the top. So turns is this command line definition, and the squiggly arrow says turn this into a program. And the way we do this is by providing implementation for each of the command line argument that we're given, and we're expected to provide a function that takes the parsed version of those arguments and returns a program. In this case, the programs are quite simple. They just print some text. Now, a common counterpoint to all of this that people will see is, well, okay, you can generate command line programs, you can generate servers, you can do all these fancy things with JSON and with type level programs. Can't you already do this with metaprogramming? And I'm going to steal a line from Conor McBride, which says, the great thing about dependent types in this case is that, yes, you can do this with metaprogramming, but here we don't even need metaprogramming because metaprogramming is programming. Everything that you can do inside the program already allows you to do the thing that you would need metaprogramming for. So you don't need to learn multiple things. You can just learn the programming language, and then you can do everything you want, including things that would require metaprogramming. And this is obviously good because then you don't have to train your software engineers to learn multiple things. All the software is tied up together in ways that don't decouple from each other in unexpected ways, etc. So we're reaching the end of the presentation, and there is a number of things we have not had the time to see. Idris is a programming language that features linear types and quantities. We've not seen this. We've seen a little bit of this where you saw a 0 here and there. That means only at compile time. This is a very important aspect of Idris that a lot of people are excited about. You can express resources and quantities in Idris in a way that you can't in other programming languages, especially when you mix it up with dependent types. Another thing that is a specific interest of me is performance and low-level programming. I'm specifically interested in using Idris for low-level programming for writing things like kernels and drivers, such that you can write in a very high-level programming language such as Idris, and also be extremely precise about the memory constraints of your platform. And finally, something we've not seen, but is also very interesting from the point of view of API definitions, is that you can write programs that expose an interface that has to follow a specific protocol. And this is also where interactive editing becomes really handy, because at each step of the protocol, you can ask the compiler, what am I supposed to do now? What are the functions that are available to me? What are the states that I'm that I'm in and that I can transition to? And all of this is possible in Idris, but we haven't had the time to see it. So I hope this is interesting enough for you to take a look, check it out. There's a website. You can install Idris on your computer. You can also use, there's a web version that you can access. We have a wiki, we have a big community. And in general, dependent types are, I hope we will see more research and efforts expanded into making dependent types usable for software rather than making dependent types for their own sake as a tool for theorem proving. Because they're both two sides of the same coin, but I feel like one side is privileged over the other. And I think that's a shame. With that said, that's the end. I would like to thank you for your attention. And if you have any questions, I'll be around for a little bit, or for a while, actually.